Good morning and welcome back. I'm Bob Wheeler, Principal Analyst at the Linley Group, and I'll be moderating the next session on advancing cloud AI. As AI accelerators are reaching their power limits, we're seeing software and system scaling becoming more critical to ongoing AI performance gains. So in this session, we'll be talking about how vendors are addressing these challenges to AI's progress, particularly in the data center. So our first talk in this session is from Groq. Our speaker today from Groq is Dennis Abts, who is Chief Architect, and he's going to be talking about delivering machine learning at scale. Dennis, if you can go ahead and share your screen and take it away.
Okay.
Okay, looks good. Take it away.
Good morning. Thank you for taking the time to attend. My name is Dennis Abts, and I'm going to be talking a little bit about how we grow from chips to systems in this talk. I was fortunate enough to give the talk at the spring conference, so this hopefully will serve as a nice follow-up to that discussion. So I hope to give kind of a brief overview of the microarchitecture and then talk about how we are scaling from chips to systems as we mature our product offering and start to ship larger systems. And so just to provide by way of motivation, some of the areas that we're looking to address here was batch size one, uncompromised peak performance. And so we'll talk a little bit about our integer and floating point performance. And not only that, but it's predictable performance in that we take advantage of determinism. And I'll talk very concretely about what that means in terms of the microarchitecture. And then lastly is talking about that scale and how we scale from one chip to multiple hundreds of chips and building scalable systems. And so we recently published our results from our initial first generation chip at ISCA this year in June. So I would encourage you to take a look and dive into the details at that publication. So just as a brief introduction, the first generation tensor streaming processor is a SIMD architecture that is a spatial architecture in that we've arranged the functional units on the chip to take advantage of their ordering of things, so that as we flow data on the chip, we literally flow the data on the chip and it flows past our functional units, and we pick up the operands and we can operate on them and produce results as they are being produced. And we can chain these together in a very nice way that allows us to exploit data flow parallelism. So I'll just kind of walk through this in more detail as we go, but I wanted to give kind of a rough layout of the chip so that we can kind of keep in mind the different functional units. We've got a matrix multiply unit, or an MXM. We've got a memory storage unit, which is split up in two hemispheres. That the memory on chip is 220 megabytes of fast SRAM. And then we've got a vector unit that sits in the center of the chip, right at the chip's bisection. And of course, this is all symmetrical. So we've got data and operands flow east and west on the chip, and instructions are dispatched from our instruction control unit, and they're pipelined vertically. So you can think of instructions flowing in this direction, in the north-south direction, and data flowing in the east-west direction. And so this organization allows us to take advantage of, for lack of a better word, kind of data flow locality, in that if we're going to move data on the chip, we want to take advantage of that as the data moves and operate on it as the data flows across the chip. And so this gives a simple example of how we're able to have a small micro program that consists of 5 micro operations, the first of which reads a vector from memory and puts it onto our streaming registers, and it starts flowing eastwardly on the chip. At time 2, we can operate on that by picking it up in the vector unit, doing some vector operation, for example, adding some bias to the weights, and then continuing to flow it into the switching unit at time 3, where we can permute the elements. and then they flow into the MXM where they are installed, and we can use them for extracting features and deep learning operations, matrix multiply, convolution, those types of operations. So in order to do this, we expose to the compiler the architecturally visible state, which is really built on this 320 lane programming abstraction. And that 320 lane programming abstraction is broken up into 20 super lanes. So in terms of the software thinks about things in terms of a 320 element vector that is used to construct a multi-dimension tensor. And that tensor is just a vector repeated in time. And so these 20 super lanes, each of which are producing 16 elements, combine to produce, well, 20 times 16 or 320 elements in each vector. The chip has 144 independent instruction queues, and these are the individual program orders that the compiler is scheduling to have complete control over the underlying hardware. And as I mentioned, the central hardware structure here is this concept of stream registers that are flowing east and west on the chip. So how do we take this and build scalable systems from it? And if you look at the outside of the die photo here, it has all the components that we just talked about. The MXM units here are on the edge, the memory units in each hemisphere, and the vector unit in the center. Around the outside of the chip, we see these C-to-C links, which are chip-to-chip links. And those chip-to-chip links provide 3.84 terabits per second of off-chip pin bandwidth. Okay, so these are 16 ports of off-chip pin bandwidth that we use to construct glueless multiprocessors. In other words, we take these chips and we strap them together by directly connecting them and building direct networks of these chips so that we can combine their collective power and take advantage of them across a larger scale system. So what does this actually look like? Well, we take the individual cards that we have built up. Our initial chip is packaged on a PCIe card. Those are packaged inside a AMD ROM system that allows us to package 8 of these systems inside a 4U chassis and allows us to get a great deal of compute density. And we put to good use 160 lanes of PCIe bandwidth, and that's PCIe Gen 4 bandwidth. So we're able to put together a tremendous amount of compute density in a relatively small form factor. And more importantly, we can control the topology of how those cards are interconnected within that node. So this allows us to support node level organizations that better support your use case. For example, if you want to strap together multiple cards to be able to support inference, you may organize these so that they're a mesh. But if you're wanting to do dense linear algebra or training, which has a more demand for all-to-all communication, you may want to organize that as an all-to-all connectivity or a different topology. The node is organized to be able to support cubes and mesh and torus networks, as well as fully connected. So the results I'm going to show today are for some fully connected networks at the node, and then these nodes are interconnected within the rack. So at the center to this is our programming model that is a logically shared address space. So we've got 220 megabytes of SRAM on each chip, and then we have multiple chips, and they share their SRAM address space. So that is logically shared, but physically distributed in a similar way as partitioned global address space, or PGAS type of programming style. So you can think about the chip as expressing this concurrency by identifying the memory concurrency within the device, within the hemisphere. And there's 44 independent slices in each hemisphere. So you can think about that as independent bank concurrency. The chip provides 176-way memory level concurrency. So we're able to take advantage of just a tremendous amount of on-chip bandwidth to be able to drive these functional units at full rate. Central to this is our software stack. So I'll come back to this in a moment, but I wanted to just kind of introduce the idea. And we've really got two paths through this in this software stack. The first path is our Groq API, which is kind of a direct to hardware developer flow, which allows us to express this parallelism in terms of layers of abstraction. The bottommost layer of abstraction is the assembly language, on top of which we build the instruction API, which allows us to have complete control over the underlying instructions that are being issued. On top of that is a Tensor API, which includes common Tensor application operations, for example, concatenating, splitting, adding, multiplying tensors. So you're able to express a tensor, a multi-dimension array, similar to how you think about a multi-dimension array in NumPy, for example, and you're able to express that and perform operations on them in a very straightforward manner. On top of that, again, we have our neural network components, and this is really your nuts and bolts of conv2D, maxpool, softmax, those types of operations that are very common in your frameworks for AI. So the idea here is that we are able to express this concurrency, and the compiler or the Groq API helps by essentially organizing these components, and then we are able to schedule them and adjust their layout in time so that they get good concurrency. And central to this idea is really the way that we do our numerical operations. And I want to take a little bit of time to kind of walk through and talk a little bit about this high performance but low precision operations. And we have a different approach to how we do our numerics, and in particular these big these large 320 by 320 these 320 by 320 matrix units here operate as either integer or floating point units. And the way that they're operating is actually producing a 320 element fused dot product. And that fused dot product allows us to produce a more accurate result, because we are literally not creating round off error on every operation. So as an example of this, this is just a very simple example to kind of tease out some of that error that gets introduced as a result of repeatedly multiplying and accumulating your results across the vector. And in particular, this just it builds upon the observation that floating point operations are not associative. In other words, if you were to take a list of floating point numbers and add them up, you would get a different number as if you took that same list but in a different order and added them up again. So to tease that out, we took NumPy with single precision FP32 and just did a simple operation that takes a random value x and squares it. So it does the multiply and then the accumulation. It does a multiply and accumulate. So this dot product accumulates, and there's a certain amount of error that gets introduced as part of this round off. And you see that our approach here of 320 element fused dot product really allows us to avoid some of that error accumulation. And the oracle here, in this case, we're comparing our FP16 data, which is accumulated as FP32. This is being compared to a FP64. So that is, in a sense, double precision. That's our baseline of comparison. And you can see that not only do we have lower absolute error, but it's also very robust. And we plot the 95% confidence interval here to show kind of how that error does in fact accumulate. And you can see that accumulation can affect, if you were to just take that list of numbers, sort them, and then add it, it's much more reliable. Obviously, that's an additional operation for that. So the sorting step here is obviously an overhead. So we wanted to compare this to kind of standard implementations, just to kind of show how numerics can really make a dramatic difference. And in particular, that cost of those numerics in terms of their performance and their power consumption is pretty dramatic. For example, a floating point add and a floating point multiply, if you're doing that in 16 bits versus 32 bits, it's dramatically different in terms of their power profile. And this is a nice summary of the different operations and the different precisions as presented by Mark Horowitz in his 2014 ISSSC keynote address. So he was really trying to motivate this killer app for high performance and low precision, and the benefits of lower precision, and certainly from their power consumption. So one of the first things that we implemented on our multi-chip system was a linear algebra solver called Cholesky. And Cholesky was implemented across 1, 2, and 4 chips to kind of get a sense of how it scales. And just for comparison here, Cholesky is an n-cubed operation. So the growth curve kind of looks like this orange line here is how the algorithm is growing. And what I'm plotting here is the actual delivered performance, and that is the number of delivered teraflops. And those delivered teraflops take into account the fact that we're doing cubically, we're doing a cubic amount of work per iteration. So just to compare that to state-of-the-art results, the most recent one I could find is by Jack Dungara and crew, and this was from GPU 11 from several years ago. But the NVIDIA P100 is plotted here, so you can see kind of the state-of-the-art. And this is really looking at it in its best way possible, and that this part of the curve is actually the left-looking, and then this part of the curve is the right-looking Cholesky performance. So it's really, this is the best known results that I could find. And this is our initial implementation on the TSP. It was this blue line, and then we further were able to take advantage of some look ahead and some performance optimization to get additional reuse and additional optimization. So we're able to improve that and get multiple factors of improvement compared to state-of-the-art GPUs. So when we have this system in a rack, and we've got these multiple TSPs, we can take advantage of the concurrency by doing either 4-way scaling or 8-way scaling within the node to be able to do strong scaling within the node and data or weak scaling, data parallelism across the nodes. So we can take advantage of your usual programming models that you use for distributed memory, whether that's MPI or MapReduce. We can take advantage of those conventional programming models and put them to good use. And at the center of all of this is our TSP chip-to-chip links, which provide fine-grained synchronous messaging. And by synchronous, I mean that we are literally synchronous across the distributed system. And this is really quite different from how normal communication models are organized, where the requester usually sends a message to the destination asking for the data, what it reads from DRAM and sends a reply. And in our model, the communication is statically scheduled by the compiler. And so the requester knows exactly at what time the data is supposed to be received, and the respondent simply sends the reply at the right time. And those reply and requests are simply reflected as send and receive instruction primitives. So very similar to how MPI uses a posted receive and a send message to send data across a point-to-point link, we take advantage of that and do the similar approach at a low level. So just to summarize kind of how we scale and walk through this packaging hierarchy, we go from chips to cards, and these cards are packaged into a dense 4U system. And then this node represents kind of the unit of computation over which we can spread strong scaling. And then the rack is a collection of nodes that are interconnected using a rack scale network. And that rack scale network takes advantage of our synchronous communication to very tightly couple all the nodes within the rack. And what this does is it allows us to build very efficient node scale systems that scale up to around 15 gigabytes of capacity SRAM capacity within the rack itself. So the compute model you can think of is you land one of these racks at your data center, and that is the unit of computation and the expansion. And you think of these 64 TSPs in the rack as operating together to solve a coordinated problem. So I want to thank you, and I hope that you choose Groq as the shortest path to performance in your deployment scenarios.